Hey, coders. Hi. Welcome to the day 6 of our spoiler free adventures. I am Jatin Kumar Malik. I'm principal engineer at Atlassian. And I am going to today walk you through a spoiler free experience of how to solve the day 6 puzzle of Advent of Code 2024. And if you're new here, I would recommend you to check my playlist for day 1 to day 5. That's because Advent of Code has a story that builds on itself, and it also has like a ladder mechanism where each day gets progressively more complex and more interesting. So I would heavily recommend you to check that out, and I promise it's going to be a fun journey for you. And before we start, do you notice something new about my display cutout today? So I'm presenting this problem to you from a hexagon because how many sides does it have? 6. And it reminds me of a joke as well. Do you know why a hexagon could not become a square? Let's just say that it had too many angles to handle. Well, enough of my nerd banter. It's day 6, and I'm sure you are eager to know more about the problem. We have a pen, we have a whiteboard. Let's get started. So the day 6 problem is called Guard Gallivant. And here's the problem. So the historians use their fancy device again, this time to whisk you all away to the North Pole prototype suit manufacturing lab in the year 1518. Interesting. So a bit of a time travel here. And it turns out that having direct access to history is very convenient for a group of historians. No wonder that's the chief historian, right? And you still have to be careful of time paradoxes. And so it will be important to avoid anyone from 1518 while the historians search for the chief. Unfortunately, a single guard is patrolling this part of the lab. And maybe you can work out where the guard will go ahead of time so that the historians can search safely. So, because we don't want to cause a paradox now, right? And you start by making a map, your puzzle input for the situation. For example, so we are given this visual textual representation of the map. So let's see this. I'll copy this here and let's increase this to make it a little big. And let's read more. How does this map work? So this map shows the current position of the guard with the tilde sign. So we can see there is a tilde sign here. And this guard is currently facing up from the perspective of the map. Okay, so because it's pointing towards up, so there is a directional aspect to it. And any obstructions create desks, alchemical reactors, etc., as are shown as the pound sign. So if you see these signs that we can see, so these are obviously our obstacles or barriers in the guard's movement. So lab guards in 1518 follow a very strict patrol protocol, which involves repeatedly following these steps. If there is something directly in front of you, turn 90 degrees right. Otherwise, take a step forward. Interesting. So I think if you have to write down, I think it's fairly simple. Keep going like in your direction. And if you see something, do a 90-degree right turn. And following the above protocol, the guard moves up several times until she reaches an obstacle. In this case, a pile of failed suit prototypes. We don't care about that. So we can see this guard was moving up, up, up. And if you see a color for the path, so they are going in this direction. They hit an obstacle. And as soon as they hit an obstacle, the rule is to turn 90 degrees right. So the guard turned right here. And yeah, so they will keep going here. Once she reaches here, she has to turn right again. So now she will start to go down. Again, there is an obstacle, turn right. Again, there is an obstacle, turn right, and so on. So the guard will basically keep patrolling. And this process continues for a while, but the guard eventually leaves the mapped area after walking past tank of universal solvent. Again, that's irrelevant, but let's follow the path and see what will happen. So we see an obstacle here. We come here. We see an obstacle here. So we turn right. We see an obstacle here. We come here. We see an obstacle here. We go up, obstacle. We go here, obstacle. And then we go down. So I think this is what they are trying to show us here, that the guard goes down from here. And what they have done is by predicting the guard's route, you can determine which specific positions in the lab will be in patrol path, including the guard's starting position. So the starting position, remember, was denoted by the tilde sign. And of course, when the guard moves up, bottom, left, right, I think their denotion will probably change for the visual representation. That may or may not be relevant for us because this is just a direction and we can find multiple ways to store that. So let's see what we have to do. So now what they have done is basically charting this on a map as a visual representation. Here is how it might look like for us. And if I make it like the final condition, like we change the color, and if I put them side by side, maybe here, and let's bring that down. Oh, shit. Yeah, so let's bring this down. We can see that it overlaps nicely with the paths that we draw. So if we keep them side by side, we can see that it's basically the representation of the same path that we took with our arrows, but instead of that, we are using the X transformation. So in this example, the guard will visit total unique number of 41 distinct positions in the map. So this 41 is basically, we are counting all the X denotions that are there and so on. And what we have to do is we are given an input, which is, I'm sure, a visual representation of this kind. And predicting the path of the guard, we have to find that how many distinct positions will the guard visit before leaving the mapped area. And if we take a quick peek at our puzzle input, we can see that it's a pretty huge maze. And here we see the guard, if you can spot that in the recording, of course. So all right, coders, this is your moment to shine. I think now is a good time to pause the video and think about how would you approach the problem. And a humble reminder is always to understand that before you think about how you would write the code, it's very important to think about how you can solve this problem manually that we just did here, and then how we can use some of the programming constructs like data structures and how do we represent this map in memory and solve that. And pause now. Seriously, don't skip this step. And I think the best way to do this is to grab a pen and paper and try to work your way through the problem. Oh, so you're still here? Okay, let me give you a couple of hints to get started. So think about what can we use to track these visited positions. So whenever we visit something, the ones that are marked by blue, we need a way to track these things. And remember, we need to count like the unique positions that our guard is visiting. Something comes to your mind? Yeah, a set, right? Maybe we can use a set to just keep a track of where and which positions the guard is going to. And the second interesting thing is that we have to find a way to represent the guard's direction. And that is fairly easy. So you can find multiple approaches of doing that. The approach I like doing is, I think I can see that this is following a simple matrix system. And we can use simple directions like we can see that your up is 0, -1. Your down is similarly 0, +1. Your left is -1, 0. And similarly, you have the right direction, which is your +1, 0. And you can see that this allows us to simply just represent the guard's direction. So I think once we have these two things, the third step that is left is the simulation. And this puzzle is really fun. This puzzle reminds me of countless terminal-based and CLI-based games I have played back when I was young, I think in the late 90s. On the computer, and it was such a fun way where you would go ahead, explore the maps. It also reminds me of this samurai type of game I used to play on my dad's first cell phone. My dad had this Garuda cell phone. Like if you're from India, and I think your parents' probably first device was a Garuda cell phone by MTNL if you're from Delhi. And even for BSNL, I think they had something similar where they had Kyocera handsets. I very well remember there used to be a game very similar like this where everything was represented like in a grid and you would move forward, meet demons, fight, and you will have a certain actions. I'll try to find that game if I can. But yeah, going back to the problem, once we have a way of keeping a track of all the positions and we have a track of keeping a sense of direction, all we need to do is we need to run a loop where we need to follow the two simple rules, where the first rule is that you keep going in the direction, like whichever direction it is. So out of all four directions, then as soon as you hit an obstacle, then is the time you basically go right. And this, remember, I think one important thing to notice here is that this right is relative to the position. So when you're moving up, the right is truly a right, like especially in this case. So if you see, this is a proper right. But when you're moving right, the right direction becomes your downward direction. And when you're moving down, your right direction becomes left. And similarly, when you're moving left, your right directions become up. So I think this is probably an edge case like where a lot of people will make mistake when writing the code, because this is something that looks very natural when we see a visual representation, but trying to write code, it's very easy to mess it up, especially when you're dealing with the grid operations with plus ones and minus ones and so on. So I think that's pretty much it, right? And yeah, while you're thinking this problem through, what I'm going to do is I'm going to go back into my VS Code and I'm going to write some code for this problem so that we can put some answers in this puzzle box right here. And let's see how quickly I can unlock the part 2. So I will see you in a bit. And we are back. So as you can see, we have received a gold star and we were able to pretty much get the correct answer in one go. I had so much fun solving this problem. What I ended up doing is I ended up printing the maze on my terminal and visualize the path of the guard. So I could see like the guard turning on each 90 degrees right on each obstacle and traversing through the path. And it was so much fun. I will try to link that. I will record a video and I will link that somewhere here. And I think problems like this reminds me the first time I started to write code and like the joys of programming, where you would write programs like this and then tinker with them to see something materialize out of thin air. Well, anyways, enough nostalgia. Let's go to the part 2. We have another star to earn. Write it down here and let's read. So it says that while the historians begin working around the guard's patrol route, you borrow their fancy device and step outside the lab. From the safety of a supply closet, you time travel through the last few months and record the nightly status of the lab's guard post on the walls of the closet. Returning after what seems like only a few seconds to the historians, they explain that the guard's patrol area is simply too large for them to safely search the lab without getting caught. Of course, we have a huge map of input data. Fortunately, they are pretty sure that adding a single new obstruction won't cause a time paradox, and they would like to place the new obstruction in such a way that the guard will get stuck in the loop, making the rest of the lab safe to search. To have the lowest chance of creating a time paradox, the historians would like to know all the possible positions for such an obstruction. This is where it gets interesting. The new obstruction cannot be placed at the guard's starting position. The guard is there right now and would notice instantly, of course. In the above example, there are only 6 positions where the new obstruction would cause the guard to get stuck in the loop. So the diagram of these 6 situations uses an O to mark these new obstructions. To show a position where the guard moves left and right, and plus to show the position where the guards moves both up and down and left and right. Okay, basically the turning position. And option 1, putting the printing press next to the guard starting position. So let's analyze the first one. So in first one, we can see that we have put an obstruction here. And if we now try to follow the path, the initial position, the guard was going up. So guard will keep going up. They will see an obstruction. They will move right. They will see another obstruction. They will go down, another obstruction. And when they come here, they will see another obstruction. That's correct. So similarly, now let's see the option 2. In option 2, what we have done is we have put like an obstruction here denoted with the red. And now if we were to track the route of the guard with the blue marker, we can see that here the guard is going up, see an obstruction, go right, then they go down, they see another obstruction, they move left, they keep going, obstruction, they go up, obstruction, they go right again, obstruction. And when they come down here, there is another obstruction. And remember, whenever there is an obstruction, the guard is supposed to turn right. So the guard turns right from here. And then here, in the first example, the loop was basically considering the initial position. But in this one, once the guard reaches here and hits the obstruction that we have placed, we can see that it will start looping in this green box like this, right? So it's, even if they took some few extra steps, after a certain point of time, they will just keep looping here in this one. And similarly, we can see some more cases here. So there is an option 3. And if we were to look at it, we can see that, yeah, so this is the loop here. I will probably draw green rectangle here. And similarly in option 4, I think we can see that this is the loop right here. In option 5, the loop is the whole, oh, this is very interesting. So here, if you see, it's not just like square or a rectangle. It's like an interesting pattern where it is following the whole path again and again. And in option 6, if we see, once the guard hits this position, it's going to basically do like a whole big wild loop. And again, what I'll do is I will add like some markers here in the post so that it's very easy for us to visualize. But let's see it further. What do we want to do now? So that we can see that in the original puzzle that was given to us, we now have 6 ways of putting an obstacle to put the guard in a continuous infinite loop, if you may say. So it doesn't really matter what you choose to use as an obstacle, so long as you and the historians can put it into a position without the guard noticing. The important thing is having enough options that you can find one that minimizes the time paradoxes. And in this example, there are 6 different positions that you could choose. You need to get the guard stuck in loop by adding a single new obstruction. How many different positions could you choose for this obstruction? So I think the question is fairly clear. We basically, in the given puzzle input, we need to find this number where we have to see like, what are the different ways where we can put an obstruction so that the guard goes into like an infinite loop. And this is your cue to pause the video, again, read the problem, get a copy and pen, write everything down and try to think. And I think an interesting hint here to note is that you probably want to build on top of the part 1 solution. Very similar approach, but I think there are few caveats where we have to do certain kind of hit and trial. If we talk about more hints, we need to watch closely as the simulation unfolds in a way, right? Like a looping path will repeat. So it's important to track where their footsteps will lead them to. And a loop is very interesting, even in these examples. So if I had to write it here, so a loop is not a loop when the guard reaches for the first time back to visited node. This is incorrect because there is a lot of time even in our part 1. Like if you see here, the guard ends up crossing the same node multiple times, right? Like 2-3 times here. So that was definitely not a loop. So going back, I think the interesting path in the definition of loop would be that you will have to somehow keep a track of the first time when you visit this node. So let's say this node is I, and if you visit it again, and in between this, all the nodes that you visited were also a repetition node, right? So giving an example here. So here, when we start this simulation and we hit this position again, the starting position, we don't know if it is a loop until we go through the path again and hit back this position. And by doing that, we basically have visited all the nodes in the last cycle once again. And I think that is the sure way of finding a loop. I think same thing is here. When you reach back, like you go here and you get here for the first time, You won't know that it is a loop until you take a whole loop around, come back to this node, and then realize that, oh, all the nodes that you have visited since visiting this for the second time, you have visited all of them for a second time. That's a loop. And I think that's my cue to leave you to think about the problem while I go back, write some code, and try to get our second star. So all the best, folks. And we are back. As you can see, we got the second gold star, and now we have completed the day 6. This ASCII art pattern keeps on getting bigger. I still cannot make out what it is, but I think by the time we reach day 15, we should have some clear picture. And about the problem, I solved it exactly how we discussed, but I did a couple of improvements actually. So I hope you were also able to solve it, but if not, let me talk about it. So remember I told you that in order to find a loop, we need to check if all the positions are being duplicated inside the loop. Well, there are a couple of optimizations that we can do and get away with it. So the first optimization I could think of was that instead of checking the whole loop, we can basically just look at the first visited node by looking at keeping a track of node plus direction. Because no matter if you're crossing the node twice, like we were doing here, you can only cross a node once in one direction. So if you're already going in one direction, and if you cross the node, the only way for you to cross the node is if you're moving in another direction, right? And the second optimization that I was able to do is, if you look at this matrix, if we do the brute force, we absolutely can do it, because in the input statement, we have 169 cross 169 grid, which again is not too big for a modern computing machine. Like even if you have a beat up 5-year-old laptop with measly 8 GB of RAMs, this shouldn't be not a problem. And remember, I'm using Python, which is single threaded, but we'll come to that. And I initially wrote a brute force solution and I was able to do it. But then when I looked back at our puzzle and how it is structured, I was able to see that there are few enhancements that we can do where we can do some pre-computation. So of course there is early exit and all of that, and I assume you know that. If you don't, you can look into my code in GitHub, and I have marked like I think where I'm exiting early. But the more interesting part is, like, since we have the grid given and we pre-computed the path already in the part 1, we very well would know that what are some of the blocks the guard is never going to go to, right? Like in an example, because we are always turning right and going internal, we can look at the paths and we can safely ignore some of the nodes that probably a guard is never going to be able to visit. And that's all. So I hope this problem was fun for you. I certainly had a lot of fun solving it. As I told you, it reminded me of my old CLI gaming days. And maybe I will put a couple of those games for you to try on in the description. Heck, even I remember this, the directional thing, there used to be something called a logo turtle programming, which used to follow the similar structure, but where you start with a triangle and then you can move them around to draw shapes. Some of you who are old enough might know what I'm talking about. And yeah, that's all for day 6. This was a fun problem. All right, I will see you guys tomorrow in 24 hours for the day 7, and happy coding. See you.